Hello friend, today we are going to start numericals on simple stress and strain. Before that, some highlights on your formulas, which formulas we are going to use while solving the numerical. First formula is, that is sigma, that is stress is equal to load upon cross sectional area. It means load sigma is equal to P by A. Sigma is denoted, that is stress, P is load and A is a cross sectional area. Cross sectional area for the solid bar we may calculate it pi by 4 into d square. If hollow circular sections will be there, then you may say area of cross section pi by 4 in bracket capital D square minus small d square. If square will be there or rectangular block will be there, then cross sectional area is equal to width into thickness. Next, strain is equal to change in length upon original length, or you may say change in dimension upon original dimension is called as strain. So according to the Hooke's law, modulus of elasticity E is equal to stress upon strain. So capital E is equal to sigma upon E, and according to that Hooke's law we have derived that equations. Change in length delta L is equal to PL upon AE. Poisson's ratio is equal to lateral strain upon linear strain. Factor of safety is equal to ultimate load upon allowable load. Another equations for the ductile materials, factor of safety is equal to yield stress divided by allowable stress. Now first numerical, write down that numericals. Concentrate here. A rod 150 cm long and of diameter 2 cm is subjected to an axial pull of 20 kN if the modulus of elasticity of the material of the rod is 2 into 10 raised to 5 Newton per mm square. Determine the stress, strain and elongation of the rod. Now from that equations, note down the given data. Length of the rod, it is given L is equal to 150 cm. Diameter D is given 2 cm converted into mm, that means 20 mm. Load P is acting 20 kN, convert into Newton, 20 into 10 raised to power 3, and modulus of elasticity capital E is equal to 2 into 10 raised to 5 Newton per mm square. Now here diameter of the rod is known, so we may easily calculate its cross sectional area. So cross sectional area is equal to pi by 4 d square. Put the value of d, that is 20 mm, so you will get here area 314.159 mm square. Now area is known, load is known, P is known, so we can calculate sigma, that is stress. So stress is equal to P by A, load upon cross sectional area. Load is given 20 into 10 raised to power 3, we have put this value here. Cross sectional area we have calculated 314.159. so after calculations you will get here sigma is equal to 63.661 Newton per mm square. That is our first answer. Second, we have to calculate its strain. Strain means modulus of elasticity is known. Stress, modulus of elasticity is equal to stress upon strain. Modulus of elasticity E is given. Stress we have already calculated. Unknown quantity is only small e. Put all this value here. Small e, strain is equal to stress upon modulus of elasticity. Sigma is equal to 63.661 we have already calculated. Modulus of elasticity which is given in the numerical 2 into 10 raised to 5. So strain is equal to 3.183 into 10 raised to minus 4. You need it is a strain, so there is no unit for it. Next is elongation of the rod, that means delta L. We have seen that equations. Strain is equal to delta L upon L. Delta L we have to calculate. Strain we have already calculated in previous equation. L is given, that is 150 centimeter. We have converted into mm, 1500 mm. So delta L is equal to cross multiplication E into L. Put the value of E, 3.183 into 10 raised to minus 4 into 1500. So delta L is equal to 0.4774 mm. It is a change in length. Now come to our second numerical. A bar of length 1.2 centimeter extend through 3 mm under the action of an axial pull of 2.4 kilonewton. Compute the strain in the material. If the diameter of the bar is 20 mm, find the stress in the bar. Means we have to, yes, figure is given, 20 mm rod diameter, which length is 1.2 meter, and tensile force of 2.4 kilonewton is acting on it. So read this problem and we note the given data. Length of the bar, that is 1.2 meter, convert into mm, 1200 mm. Extension of the bar is nothing but it is a change in length. Extend through 3 mm. It means it is a change in length. Delta L is equal to 3 mm. Axial pull of load is acting 2.4 kilonewton. Convert into Newton. 2.4 into 10 raised to power 3 Newton. Diameter of the rod is given 20 mm. So it is a solid rod. So again we may calculate its cross sectional area. Cross sectional area A is equal to pi by 4 d square is equal to pi by 4. Put the value of d here, 20 into bracket square. You will get an answer here, 3.14.159 unit mm square. Now compute the strain in the material. Strain means small e, or you may say epsilon. Small e is equal to, we know, delta L upon L. Change in length upon original length. Change in length already given in the numerical, that is 3 mm. Original length, that is 1.2 meter, we have converted into mm, that becomes 1200 mm. We have put here this value 1200 mm. So we will get here small e strain is equal to 0.0025. It means 2.5 into 10 raised to minus 3. It is a strain. So again here remember there is no unit. Now here we have to calculate stress. To calculate the stress, our equation is stress is equal to load upon cross sectional area. Load is given 2.4. We have converted into Newton. So 2.4 into 10 raised to power 3 Newton. Cross sectional area we already calculated, 314.159, 314.159. If we put this value and do the calculations, so sigma is equal to 7.6394 Newton per mm square. 7.6394 Newton per mm square. Newton per mm square, you may write here megapascal also. You may write here megapascal also. Okay. Now come to our third numericals. We will go there. A hollow cast iron cylinder 4 meter long, 300 mm outer diameter and thickness of metal 50 mm is subjected to a central load on the top when standing straight. The stress produced is 75,000 kilonewton per meter square. Assume Young modulus for cast iron as 1.5 into 10 raised to 8 kilonewton per meter square and find magnitude of the load. Second, longitudinal strain produced, and third, total decrease in length. Now concentrate here. It's a hollow cast iron cylinder. Hollow cast iron cylinder having 4 meter length. So outer diameter of the cylinder, capital D, is given to you 300 mm. Here value is given in stress is given in kilonewton per meter square. So we will consider here, we may convert this mm into meter to avoid the mistake. Thickness of the metal is 50 mm. Thickness of the metal 50 mm is given, convert into meter, so divide by 1000. 1 meter is equal to 1000 mm. Remember, 1 meter is equal to 1000 mm. Is it right? So outer diameter is known 300 mm. Thickness is known 50 mm. So we can calculate here inner diameter. So inner diameter of the rod small d is equal to d minus twice t. So you will get here inner diameter 0.2 meter. So here stress produced, already mentioned in the numerical, 75,000 kilonewton per meter square, and modulus of elasticity for the cast iron, capital E, is equal to 1.5 into 10 raised to 8 kilonewton per meter square. And now we have to calculate magnitude of the load. First, so sigma stress is given, outer diameter, inner diameter is known. So with the help of this we can calculate its cross sectional area. When hollow section will be there, so cross sectional area is equal to pi by 4 into capital D square minus small d square. Capital D indicates it is a outer diameter, small d indicates it is a inner diameter. Okay, so our basic equation is sigma is equal to P upon A. So cross multiplications will be there. P is equal to sigma into A. Sigma is given to you 75,000, capital A, cross sectional area pi by 4, capital D square minus small d square. Capital D square is 0.3 meter and small d is equal to 0.2 meter. So 0.3 bracket square minus 0.2 bracket square. Here you will get here P is equal to 2945.2 kilonewton. This is our first answer, magnitude of the load. Now in the secondary we have to calculate longitudinal strain induced in the cylinder. So strain is equal to, according to the Hooke's law, capital E is equal to stress upon strain. Again we reform that equations, rearrange. E is equal to, strain is equal to, small e is equal to stress upon modulus of elasticity. Stress means sigma upon small capital E. Sigma is given to you, that is 75,000, and capital E is also given 1.5 into 10 raised to 8. So longitudinal strain small e is equal to 0.0005. This is our second answer. And third, we have to calculate total decrease in length. Decrease in length means change in length. So strain is equal to change in length upon original length, that is delta L upon L. Here we have to calculate change in length. Total decrease in length is nothing but it is change in length. So 0.005 strain we have already calculated is equal to delta L upon L. L is equal to 4 meter. It is already given in the numerical. So after doing this cross multiplications, delta L is equal to 0.005 into 4 is equal to 0.002 meter. Convert into mm, so it is equal to multiple by 1000, so you will get here 2 mm. So first answer, magnitude of the load, that is 2945.2 kilonewton. Our second answer, longitudinal strain, small e is equal to 0.005, and third answer, total decrease in length or change in length is equal to 2 mm. Next numerical, a wooden tie 8 meter long, 100 mm wide, 120 mm thick is subjected to an axial pull of 50 kilonewton and strength is 4 mm. Calculate the value of E for the material. E is nothing but it is modulus of elasticity. Figure is given. So in that case 50 kilonewton tensile force is acting, 100 mm, 8 meter length is given, 100 meter, 100 mm wide and 120 mm thick. So given data, length L is equal to 8 meter, so it becomes 8000 mm. Width W is equal to 100 mm. Thickness T is equal to 120 mm. Load P is equal to 50 kilonewton. Convert into Newton. 50 into 10 raised to 3 Newton, and change in length delta L is equal to 4 mm. Delta L is equal to 4 mm. This is the given data, and now we have to calculate modulus of elasticity E. So we will see step by step. Capital A means cross sectional area of this section's wooden tie is equal to width into thickness. So width is given 100, thickness is given 120. So cross sectional area is equal to 12,000 mm square. Now stress is equal to load upon cross sectional area. Load is given, cross sectional area we already calculated. So put here value. Load P is equal to 50 into 10 raised to power 3 divided by cross sectional area 12,000. So sigma is equal to 4.166 Newton per mm square. Now we have to calculate E, capital E, that is modulus of elasticity. So we know this strain equations. Again, strain is equal to delta L upon L. Delta L upon L, change in length upon original length. So small e is equal to delta L is given 4 mm, L is given 8000 mm. So small e is equal to 0.0005, means 5 into 10 raised to minus 4. It is a strain, so there is no unit. And capital E is equal to last modulus of elasticity, stress upon strain. Stress we already calculated, strain also we have calculated. Stress is equal to 4.166 divided by strain 5 into 10 raised to minus 4. So modulus of elasticity for this wooden block is equal to 8333.2 Newton per mm square. Now here we have solved that numerical step by step. Instead of that, you may solve this numerical in one step also. Here we know the equations. Previous equations we have seen. Delta L is equal to PL upon AE. We know that equations. Good. PL upon AE. Delta L is equal to PL upon AE. Delta L is known, that is 4 mm. PL upon AE. P is also known, 15 to 10 raised to power 3. L is also known, into 8000. Divided by cross sectional area we have already calculated 12,000. Unknown quantity will be only capital E. In one step you may calculate this modulus of elasticity. Is it right? Okay. Now come to next numerical. A circular pipe of internal diameter 30 mm and thickness 4 mm is subjected to a force of 30 kN and elongation was measured as 1 mm. If the length of the pipe is 2 meter, find the value of Young modulus of elasticity and stress in the pipe. Read this numerical carefully. A circular pipe of internal diameter and thickness is given. It means it is a hollow pipe which having internal diameter small d is equal to 30 mm, thickness t is equal to 4 mm, is subjected to force of 30 kilonewton. P is equal to 30 kilonewton. Convert that P into Newton. So 30 into 10 raised to power 3 Newton. Elongation was measured as 1 mm. Elongation is nothing but it is a change in length, that is 1 mm. So delta L is equal to 1 mm. If the length of the pipe is 2 meter, length of pipe is given 2 meter, L is equal to 2 meter, convert into mm, that is 2000 mm. Find the value of modulus of elasticity, capital E we have to calculate, and stress in the pipe, capital E and sigma we have to calculate here. Now first, stress in the pipe material. Stress sigma is equal to, we know, load upon cross sectional area. Load is given, that is 30 into 10 raised to power 3 Newton. Cross sectional area, here we have to calculate cross sectional area, pi by 4 into inner diameter is 30 small d and outer diameter thickness small d plus 2t, it becomes 38 mm. So outer diameter is equal to, capital D is equal to 38. So pi by 4 into 38 bracket square minus 30 bracket square is equal to 427.26 mm square is the cross sectional area of the circular pipe. So put this value here, you will get the stress 70.2 Newton per mm square. Now according to the Hooke's law, capital E modulus of elasticity is equal to stress upon strain. We already used that equation so many times. Stress is, we already calculated, 70.2 Newton per mm square. Strain is equal to 5 into 10 raised to 4 delta L upon L. Delta L is given to you 1 mm. Length of the cylinder, that is 2 meter, that means 2000 mm. So 1 upon 2000, it becomes 5 into 10 raised to minus 4, that becomes strain. Put this value here, strain, you will get here modulus of elasticity E is equal to 140.400 Newton per mm square, or you may say 140.4 gigapascal. Is it right? Now come to the next numerical. A punch for making holes in a steel plate as shown in figure. Assume that a punch having a diameter D is equal to 20 mm. This diameter D is equal to 20 mm is used to punch a hole in a 8 mm plate as shown in cross sectional view. If a force P is equal to 110 kilonewton is required to create the hole, what is the average shear stress in the plate and average compressive stress in the punch? Now observe that figure. Here plate is given to you. This is the punch, and here from the top side force is applied, force of 110 kilonewton is applied from the top side, whereas diameter of this punch is 20 mm and the thickness of the plate is 8 mm. This cross sectional view, another in the views we are getting this clearly. So The shear area is equal to circumference of the hole times the thickness of plate. Means shear area, this area will be shear off here, this area will be shear off. Means if we have to shear off that area, if we say here this area we have to shear off. So this is the circumference, this is the circumference of that punch hole we may say, and this is the thickness of that plate, this thickness of the plate. So this circumference of this area, circumference is equal to pi d, we calculate it pi d into its thickness t. Pi d, this is the circumference and t is the thickness. So we may say pi d into t, it is the shear area. So put this value here, pi, diameter of the punch is given 20 mm and thickness is given 8 mm. So answer, shear area is equal to 502.7 mm square. After knowing the shear area, we can easily calculate its shear stress. So again, shear stress is nothing but it is load upon cross sectional area. Load we know 110 kilonewton and area is equal to 502.7 mm square. After doing that calculations, you will get here 219 megapascal, Newton per mm square. Here you have to convert that kilonewton into Newton. 110 into 10 raised to 3 divided by 502.7 mm square. Now next we have to calculate its compressive stress in the punch. Sigma c is the compressive stress, and again stress is equal to basic equation load upon cross sectional area. Now here remember, concentrate to this point, average compressive stress in the punch means we have to calculate the stress in that section. We have to calculate the stress in that section. So when the load will be acting on it, compressive stress will be induced in these sections. So area of this section will be pi by 4 into d square, area of punch pi by 4 into d square. So P divided by pi by 4 into d square. So you will get here 350 megapascal. 350 megapascal. Now our next numerical, it's a very simple numerical. A prismatic steel bar 700 mm long is stretched 0.7 mm by a tensile force P. Find the magnitude of P in kilonewton if volume of the bar is 450 into 10 raised to 3 mm cube and modulus of elasticity means capital E is given 210 gigapascal. Now concentrate here. Give your attention. Prismatic steel bar 700 mm long, length is given 700, is stretched 0.7 mm. Stretch means it is a elongations, or you may say it is change in length by a tensile force P. P is unknown, P Newton, N indicates it is in Newton. Find the magnitude of P in kilonewton. We have to convert into kilonewton. Now here volume of the bar is given 450 into 10 raised to 3 mm cube and modulus of elasticity is 210 gigapascal. Now given data again, note length L is equal to 700 mm, change in length delta L is equal to 0.7 mm, modulus of elasticity 210 gigapascal, convert into Newton per mm square, so multiple by 10 raised to 3, 210 into 10 raised to 3 Newton per mm square. Now here volume V is equal to 450 into 10 raised to 3 mm cube, load P is equal to P is unknown quantity. We have to calculate the value of P. Now volume is equal to cross sectional area into length. You already studied in previous class also. Volume is equal to cross sectional area into length. So if we do this, rearrange this equation. So cross sectional area is equal to volume upon length. Volume is equal to 450 into 10 raised to 3, which is given. Length is equal to 700. It is also given. So cross sectional area capital A is equal to 642.857 mm square. Now next, delta L is known. So delta L is equal to PL upon A. In previously we have solved the numerical step by step. Stress we have calculated, then strain we have calculated. Now I am using here direct relation, delta L is equal to PL upon AE. So again rearrange that equations. We have to calculate the P. So P is equal to delta L into AE divided by L. Delta L is given to you, that is 0.7 mm. Cross L is equal to cross sectional area we already calculated, 642.857. E 210 into 10 raised to 3 divided by L. L means 700 mm. It is given in the numerical. So after doing these calculations, after this you will get answers. P is equal to 134.999 into 10 raised to 3 Newton. But answer should be is in kilonewton. So here to convert the Newton into kilonewton, divide by 1000. It means 10 raised to 3. 10 raised to 3. 10 raised to 3 will be cancelled and your answer will be 134.999 kilonewton. Okay. Now this is the next example, which is practical base. It's a very good example. A car weighing 130 kilonewton when fully loaded is pulled slowly up a steep inclined track by a steel cable as shown in the figure. The cable has an effective cross-sectional area of 490 mm square and angle alpha inclination, that is the inclined angle of that plane, it is 30 degree. So calculate the tensile stress sigma T in the cable. T indicate that is tensile. Stress we have to calculate. Stress induced in the tensile bar. So now you may observe that thing. This is the trolley and it is lifted from bottom ground to upper side with the help of that cable wire rope at an angle 30 degree. Angle is given 30 degree. Now first we will see its free body diagram. If we say here free body diagram, compare that figures. This is the plane. This plane is given. When it moves in upward direction, so tensile force is acting in the upward side. Alpha, that is 30 degree, angle is given. 30 degree is the angle of inclination. His roller support are there. So when support are there, so we may say there is a reactions acting R1 and R2. You already studied in engineering mechanics, reactions acting at the roller support at a point, this one point. So these reactions R1, another reactions R2, and total weight of that car, total weight of this car, you may say trolley, is acting in the downward direction, that is acting in downward directions. So according to this, W is equal to weight of the car, T is the tensile force acting in the cable, alpha is the angle of inclination, and capital A is the effective cross-sectional area of the cable. Now according to your basic fundamentals of equilibrium, stress analysis here, T force is acting in the right hand side, this W is acts in the downward direction, this angle is alpha, this angle is alpha. So when that force, we resolve that W into two components. So one component will be W sine alpha, in these directions. This direction, W sine alpha acts in downward side. So after taking the equilibrium condition, T is equal to W sine alpha, or you may say T acting in right hand side, W sine alpha is acting in opposite direction. So you may say T minus W sine alpha is equal to 0. It means T is equal to W sine alpha. T is equal to W sine alpha. So we have to calculate the tensile stress in the cable. Stress is equal to P load upon area. So which type of load is acting here? Tensile load is acting. Tensile load is nothing but it is, in this case it is T. So what is the value of T? W sine alpha divided by cross sectional area A. So W is known, that is 130 kilonewton. Car weighing is given. Alpha is known, 30 degree. Cross sectional area 490 mm square, which is already mentioned in the numerical. So we have to put only values. Sigma T is equal to 130 into sine 30 divided by 490 mm square. You have to convert into 130 into 10 raised to power 3. So you will get here answers 133 megapascal. Answer is 133 megapascal tensile stress induced in the wire cable. Now this another examples on practical. It is also in your application base. You already use this clutch lever. So a force P of 70 Newton is applied by a rider to the front hand brake of bicycle. P is the resultant of an evenly distributed pressure. Evenly distributed pressure means uniform distributed load, you may say. As the handbrake pivots at A, a tension T develops in the 460 mm long brake cable, which area is 1.075 mm square, which elongates by delta. Which elongates by delta is equal to 0.214 mm. 0.214 mm. Find the normal stress sigma and strain in the brake cable. Now figure is given here. Now see that figure. If we see here figure, in that case force P is acting, that is the resultant 70 Newton force is acting, and that section is given, that is the gripping actions of that side. So this action, this load, that is 50 mm. This is 50 mm from that side to this side. We having the brake lever in that case. Is it right? So this is the sections for that. P is acting. Bicycle, here cable torque, T is applying here, tensions will be there. When we operate this lever, this cable will be pulled and tensile force acts on it and tensile stress induced in that cable. When we applying the force at that time, this cable elongates means change in dimension, change in length by 0.214 mm. So now here we will note down the given data. P is equal to 70 Newton. Cross sectional area of this cable which is shown in the red color, 1.075 mm square. Length is 460 mm. The length of that cable is 460 mm, which is already mentioned in the figure also. Delta is equal to 0.214 mm. Now here, and this lever is operated about the point A. Now your studied is moment. Now listen here. This, if we say that this one beam, this distance from the force to the application of point, that is 100 mm, this 50 mm, and uniform distributed load is always acting at the center of the span. So remaining 100 mm minus 50 mm, so this distance become 50. This distance become 50. Is it right? This distance become 50 and it is acting at the center. So it becomes here 50 plus 25. 50 plus 25. So it becomes 75 mm. Okay. Now T is acting here. So the distance, the T is nothing but it is the force, tensile force acts on the cable. And in that side, this dimension, perpendicular dimension is 37.5. So we have to take moment. Moment is nothing but moment is the force into perpendicular distance up to that point. Okay. Now force P is acting here. P into this distance 50 plus 25. How much? This is 75 mm. So moment P into 75. P into 75 is equal to T into this distance from the T to pivot 37.5. So equation T into 37.5. So our equation becomes P into 75 is equal to T into 37.5. So in that case you will get here T is equal to twice P. You will get here T is equal to twice P. Now tensile stress is sigma is equal to T upon cross sectional area. So sigma is given. Sigma we have to calculate. T means it is 2P. P is given to you 70 mm. So 2 into 70. 2 into 70 divided by its cross sectional area, that is 1.075. It means that equation sigma is equal to 2 into 70, that is 140 divided by 1.075 mm square. After calculations, sigma is equal to 103.2 megapascal. Now, is it clear? Sigma. Now strain, next point is strain. Strain is equal to change in length upon original length, delta L upon L. So delta L is equal to already given 0.214 mm. Here notation they have used delta. It is actually delta L. Delta L upon L. So epsilon E is equal to strain is equal to 4.65 into 10 raised to minus 4. And now last, modulus of elasticity is equal to stress upon strain. Stress is given 103.2 megapascal or Newton per mm square divided by 4.65 into 10 raised to minus 4. So modulus of elasticity of the cable material is equal to 1.4 into 10 raised to 5 megapascal. Now come to our next numerical. A circular aluminum tube of length L is equal to 400 mm is loaded in a compression by forces P as shown in the figure. The outside and inside diameter are 60 mm and 50 mm respectively. A strain gauge is placed on the outside of the bar to measure the normal strain in the longitudinal direction. If the measured strain is 550 into 10 raised to minus 6, then what is the shortening delta of the bar? Delta is nothing but it is change in length. Second, if the compressive stress in the bar is indented to by 40 megapascal, then what should be the load acting on the bar? Okay, now see that figure. Rod bar is given, compressive force is acting on it, length of the bar is given, aluminum tube, it is L is equal to 400 mm. This is a tube which having diameter, outer diameter capital D, 60 mm, or you may say, and another is 50 mm diameter. So here we may calculate this cross sectional area. Capital A is, we may calculate pi by 4 into 60 bracket square minus 50 bracket square. Now compressive force is acting on it. So shortening of the bar is equal to delta L is equal to epsilon into L, means again basic equation, strain is equal to delta L upon L. Here I have taken directly that equations. Delta L is given to you directly. Change in length is directly given to you. 550 into 10 raised to minus 6, and length of the bar is 400 mm. So delta L, change in length, is equal to 0.220 mm. Second, we have to calculate stress. Compressive stress in the bar, it is given 40 megapascal. Sigma compressive stress is already given in the numerical, 40 megapascal. Cross sectional area, pi by 4 into 60 bracket square minus 50 bracket square. So sigma is equal to load upon cross sectional area. Rearrange that equations. Cross P is equal to sigma into A. Sigma is given 40, whereas area is equal to 4863.9 mm square. Directly I have taken that area. So P is equal to 34.6 kilonewton, or you may say 34.6 into 10 raised to 3 Newton. Now this next example, the yoke and rod connection is subjected to a tensile force of 5 kilonewton. Determine the average normal stress in each rod. There are two rods, and the average shear stress in the pin A between the members. Now see this figure. 5 kilonewton force is acting at the both end. There are two rods, one having diameter 30 mm, another rod having the diameter 40 mm. Diameter is different, and both this rod, this is called yoke, and both these sections, this rod and this rod sections, yoke connected with the help of that pin A, which having the 25 mm diameter. So first we will consider first rod, 40 mm diameter. When the stress we have to calculate here for 40 mm diameter. So stress in the 40 mm diameter, again basic equation, load upon cross sectional area. Load is given 5 into 10 raised to power 3. Cross sectional area pi by 4 into d square, means 40 mm square, 3.98 megapascal. We have done that equation. Otherwise you may say directly Newton per mm square also. Similar way for 30 mm diameter. Sigma 30, we have written here, means it means the stress induced in the 30 mm bar. Here P upon A again here. Instead of that, to indicate we have defined, take another notations, but we may take here P upon A. P means 5 into 10 raised to 3 divided by pi by 4 into this 30 mm bracket square directly. Here no need to convert, you don't convert this into meter square. You may directly write in pi by 4 into 30 mm square. So you will get the answer directly, 7.07 Newton per mm square. And average shear stress for the pin A, this pin A. So cross sectional area of that pin is pi by 4 into 25 mm bracket square. So P force is acting on it. Now here P by 2 force is acting 5 kilonewton. This side also 5 kilonewton. Here two forces are acting, in that side 5, in that side 5. So P by 2, P by 2. So P by 2 means 2.5 into 10 raised to 3 divided by pi by 4.25 bracket square. So this 5.09 megapascal. This is our next numerical. average shear stress in each of the 6 mm diameter bolt and along each of the 4 shaded shear planes is not allowed to exceed 80 megapascal and 500 kilopascal respectively. Determine the maximum axial force P that can be applied to the joint. Now here observe that things, two plates are there, two plates connected with the help of another plates which having bolted by 4 bolt. At one time 80 megapascal stress is induced and another side 500 kilopascal stress is induced in that case. So shear area of that bolt, the diameter of the bolt 6 mm, there are 4 bolt, so pi by 4 into 0.006 we have converted into meter, so you will get the area of bolt 28.274 into 10 raised to minus 6 meter square. This is the area of one bolt. Now area of plate 100 by 100 section is given to you here, so 0.1 into 0.1 convert into meter, so that becomes 0.01 meter square of that area of that sections. So shear stress at the bolt. Now here total load P is acting on it. How many bolts are there? 4 bolts are there. So one bolt load per bolt means P by 4. Load per bolt is equal to P by 4, and at first case 80 megapascal stress is induced. So shear stress is equal to load upon cross sectional area of the bolt. So stress is equal to 80 into 10 raised to 6 P by 4 divided by 28.274 into 10 raised to minus 6. So P is equal to, after doing that calculations, you will get 9047 Newton force is acting in the first case. In another second case, shear stress induces 500 kilopascal. 500 kilopascal means 500 into 10 raised to 3 Pascal. Pascal Newton per meter square. You have seen that conversion. P by 4, against P by 4 means load acting per bolt and its cross sectional area of that plate 0.01 meter square, 0.01. So in this case 20,000 Newton force is acting in that case. Okay. Now if you have any problems, write your problems in the comment sections or in the chat. We will solve your queries. Okay. Thank you.